let me just start recording just so this is there as well. We are very much going to talk about why factoring belongs in a module with solving equations, even though I'm going to ask you to do those or to demonstrate those two skills separately. So we are going to look at them as almost two separate topics, but the tool of factoring is something that we use all the time for solving equations and for understanding equations, and therefore for understanding functions, which is where we're headed with graphing. So it's all very tightly connected. And this module very much builds on what we talked about in algebra basics. We don't spend a ton of time with the exponents part of it, though exponents always kick around in some manner. Exponent rules never really get left by the wayside. But we're primarily going to focus on talking about terms and factors and how to manipulate algebraic expressions. We revisit fractions, except this time, instead of adding and subtracting fractions, we end up solving rational equations, which just means equations that contain fractions, particularly those that have x's in the denominator. Algebraic fractions is another way to think of those. Today is going to be all about factoring. So we'll do a little bit of why we are factoring, just to refresh your memories there. I'm sure you've used this technique, but I want to remind you why we bother covering it in this course. And this may well be a refresher for you. Let me know where we're at any time. We're going to start with common factoring because it is, in a sense, the most important kind of factoring you can do, because it's the first thing you're going to try to tackle with any factoring question. We'll talk about a difference of squares, which some of you have already pointed out. You're comfortable with those. We talked about conjugates in exponents and radicals. We've already played with this idea in another context, and then we'll we'll dig into trinomials. As with any algebra, if you have a favorite way of completing any of these questions, go right ahead. I'm happy to talk about those in class if you want to share them with each other, share them with me, or just go ahead and do what you do. There's so many different approaches. You're always welcome to use your favorite. As soon as we get into factoring trinomials, you'll know exactly what I mean. And I've seen all sorts of different approaches, all good. I know some of you are very comfortable with factoring. I saw you factor already in modules where the only reason you weren't supposed to factor is that technically we hadn't covered it yet. So I know that that's out there. I don't know who did my survey. I did post an announcement with it was just a SurveyMonkey survey, completely anonymous, right before the break. I posted it to all of my classes, so I don't know where all of the feedback came from, but I did have a look at some of those responses. So I just asked you what topics you had accessed in Brightspace, and of those topics and tools that you accessed, which ones were helpful, and which ones, if any, actually hindered your learning? Were any of the ones taking away from the material for you? And generally, it seems like what's available there is helpful. You're either here in the live class or you're watching the recording afterwards. Maybe you're watching some of the pre-recorded videos. It looks like the accompanying slides for the Zoom classes have generally been helpful, so I will continue to do those. Those are new this term. And I had one comment that you'd like to see. Again, I don't know which class, the annotations that I do on the screen. So I'm going to see if I can make this happen within Brightspace, or within PowerPoint without crashing the system. So I've played around with that this week. We haven't had the opportunity really to use breakout rooms in this class because there's just not enough time to really think. I feel like I do have to push material a little bit. So I imagine you haven't missed too much based on how people feel about breakout rooms. As always, if that's something that you'd like to be doing more of, we can. We are a fairly small group. It's quite different from my 40-person classes. And I don't, again, know where it's coming from, but the additional resources tend to be a hindrance, if anything. So the extra videos or extra websites. So it tells me not to put a lot of my energy into this necessarily, or it tells me to put more energy into it to make them better. I don't know where that needs to go yet. So if you have any feedback for me, if this is maybe one of your comments, if you said that some of the additional resources were a hindrance, by all means, let me know how that could be improved, or if they're just not something that you're using. So there's no wrong answers here. I just wanted to share a little bit of what I saw with that survey. It's still open. It remains open. It sends me an email when someone replies. It's completely, when any answers come in, again, it's completely anonymous. So if it is something you'd like to do from now until the end of the semester, you're always welcome to do that. All right, and I thought with that, we would dive right in. Any thoughts, any questions? Welcome to week 9. We do have a 14-week semester, but we count to 15. Last week was week 8, so we do fully skip that one. All right, are we ready? Let's do it. I guess basically, if I say factoring, are you like, yep, we're good, I'm very comfortable with this, or a little bit like, ooh, I'm going to need a refresher? How are you feeling on the outset before we get started with this topic? So is factoring kind of a, yes, this is awesome, or less comfortable, maybe responding with a reaction or letting me know? So far, we're on the up. Okay. No one's letting me know that this is scary. You can always send me a chat privately at any point. Okay, let's do it. Why do we factor? Well, it's just another tool. Fundamentally, it is just another tool in the kit to manipulate expressions, and particularly those ones within equations, within systems, so that we have yet another set of tools open to us. Algebra basics, so you guys know this. We went forwards. So we used distributive property of a monomial times a binomial, or we multiplied two binomials together. So here we had x squared plus 5x plus 6. Whether you did that in one step or in 2 steps, we all got to that answer. Saw lots of good ones there. And this was always under, if we talked about it with language, we said we were looking to simplify often. That's some of the language we use there. Sometimes we said expand. Simplify is sometimes a little bit misleading because when we factor, a lot of the goal is also to simplify. So what you'll see is we've just created the expressions that we initially simplified. So 2x plus 14 is equal to 2 times x plus 7. So now we can absolutely just go back and forth. And this is the second piece is, of course, what we're looking at here. We'll spend a fair bit of time looking at trinomials. These are easier trinomials where the coefficient of the x squared is equal to 1. We'll also look at trinomials where the coefficient of x squared is larger than 1. That's one of the main, that's probably the trickiest set of factoring problems that we'll look at. So this just lets us go backwards. Factoring lets us go backwards from simplifying or expanding. And the reality is we've already been presented with questions that are factored. We've dealt with factored expressions. We just haven't had to do the factoring on our own. So we saw this in algebra basics. This is directly poached from the test. We saw that if we have one term in the top and one term in the bottom, we can cancel factors. And here we said, for example, that we have matching factors 8y plus 1, so those canceled. 4 and the 6, we looked at those and said both are divisible by 2, so we end up with 2 and 3. And we used our exponent rules to move that y down to the denominator. And the 8y minus 1 is unique. So we already tackled the concept that we need for this. We're just now going to start one step earlier. So for example, we might have a question that actually looks like this. Let's say 32y plus 4 divided by, what do I want to do here? 48y cubed plus 6y squared. If we start with this expression, this is now what we're tackling as part of this module. This is really how we encounter these in the wild. We've done some sort of mathematics. We maybe put some equations together. Who knows where this is coming from, but now we end up with a series of terms in the numerator, a series of terms in the denominator. So hopefully you recognize 2 terms in the numerator, 2 terms in the denominator. And then the problem is that you can't cancel terms. I can't just say, oh, 4 and 6 are both divisible by 2. You might notice that the 32, the 4, the 48, and the 6 are all divided by 2, and then you'd be onto something. But as written here, we absolutely cannot just simplify. But what we do here is recognize that these are factorable expressions, so we return these to where I just stole them from. So 4 times 8y plus 1 would be the factored version of the denominator, or sorry, of the numerator. And here we have 6y squared actually is equal to 8y plus 1. Now I have one term in the numerator, one term in the denominator. Now I can start to cancel the factors. So basically, we need this tool because generally our problems that we actually encounter aren't as tidy as they were in algebra basics. That's my point here. So we do revisit this. The other thing that we did in algebra basics was add and subtract rational expressions. In order to do that, we looked at all of our denominators and made sure that we had equivalent fractions to these that all had the same denominator. And we want that denominator to be the lowest or the least common denominator. Right? In order to add and subtract, we need them to have the same denominator. What is that denominator? Well, the denominator that's the least, the smallest value that is still contains all of these factors, that still contains all of those factors, means that we have to know what the factors are. Right? We have to find the least common denominator. We looked at the factors of the denominators. Well, usually the denominators aren't in this form. They are currently in factored form. There is one term here, one term here, and one term here. Usually our denominators look more like this: 8x plus 12 and 48x minus 12. And when they look like that, I can't tell what the common factors are. So again, in this particular module, we're not going to be just adding and subtracting these expressions. We're going to have equations that maybe look like this. So these three fractions equal to 1. And our job is then to solve for x. Now, it's very similar to the process of adding and subtracting. We're still going to be looking for the lowest common denominator. We're just going to do something different with it, but we still want the lowest common denominator. But now we have to be very aware that if our denominators are not yet factored, that we have to factor them first. In order to solve that equation, we're going to have to be able to factor those denominators. And then the last piece, this is the next module, is to play with this function and to look at a picture of this function, to visualize this function. Factoring is an awfully handy tool. While we're here, this function, y is equal to x squared minus 5x plus 6, what shape is that? If I draw a picture of this, what am I going to get? What do you think? It's all based on that highest term. It's raised to the power of 2. In other words, it's quadratic. I suspect more folks than are willing to admit it know what's going on here. If I have x to the power of 2, this is a quadratic function. It's a parabola, right? It'll look something like this. It'll either open upwards or open downwards. This one actually opens up. We're going to learn to read that, or relearn how to read that, how to be comfortable with that. And this particular one actually sits roughly like that. So we'd need to find the vertex, the critical point here, that is the minimum point. But other pieces that I can look at quite quickly is, where does this function, this relationship between x and y, cross the y-axis, and where does it cross the x-axis? So if I ask that question, let's start with the y-axis. So not strictly speaking part of this module, but we're getting there. We're going to head to graphing anyway. If I want to know where exactly that point is, where we cross the y-axis, I'm really looking for the y-intercept. And that happens where x is neither to the left nor to the right. It happens where x is equal to 0. So that one's pretty easy. If I set x equal to 0, so if I take my x's and I throw in a 0, I find that y is equal to
6.
6, yeah. So it does cross the y-axis at the point 0, 6. So that's the easy one. That's always going to be the easier one when a quadratic is written in this form. What about the x? Well, what I can see here from this not super accurate picture, but I promise you it looks something like this, is that we actually cross the x-axis twice at 2 different points. So what are the x-intercepts? Well, those happen when we set y to 0, when we're neither above or below the x-axis, when we're sitting right on it. So now we have y equal to 0, and that gives us 0 is equal to x squared minus 5x plus 6. And this one's trickier. It didn't just give us a single numerical answer. Now we have both an x squared and an x. So yeah, this takes us into solving equations and what it is we're trying to do here. And we're definitely going to solve equations like this in this module and in the next one. We just have slightly different applications. So how do I solve for x in this case? Two strategies. Do you remember your quadratic equation? Quadratic formula, rather. Given that 0 is equal to something that looks like this, that's in the form of ax squared plus bx plus c, well, that means that I can solve for x by calculating the value of negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. That, if I take a equals 1, b equals negative 5, and c equals 6, that will pop out the values for x. That will always work. And we'll do that in case you need a refresher. But this particular expression on the right-hand side is factorable. I can rewrite it as a single term with the factors x minus 2 times x minus 3. And if you expand that, you'll see that I'm right. And now that we're in factored form, it is so much easier for me to decide what values of x will make the right-hand side equal to 0. In other words, what values of x make the equation true, make the left side equal to the right side.
2 or 3.
Yeah. Think of putting 2 in for the value of x in the first one. I don't even care what the next bracket is. If the first bracket is 0, 0 times anything is 0, the entire right-hand side is 0. So x equals 2 is a solution to that equation. What's the other one? You had mentioned it, Eunice, sorry?
Yeah, 3.
Yeah, 3. Because if I put x equals 3 into the second factor, we're good. That's hard to guess at this stage, but it's easy to guess down here. So where do we cross the x-axis? Well, we cross it, I didn't draw it very nicely here, at the point x is equal to 2 and x is equal to 3. We're not at all worried about graphing, but we are going to take expressions that look like this and solve them, either using the quadratic formula, or if they're factorable, it's much faster to factor. So that's the why. That's the why we're going to spend the time on factoring today that we're going to spend. Again, we'll look at these ones first, and then tomorrow we'll actually apply them to expressions and get back to the idea of solving equations. So given that we only have an hour and a half, we won't get all the way through today. All right, we start with common factoring because what I want you to remember, if nothing else from today, is that the very first type of factoring you should look for is always common factoring. Whatever else, whatever other pattern you might be seeing, you want to make sure you've checked for common factors. What the heck are common factors? Well, to find common factors, we first have to acknowledge that we have 3 terms here. This isn't mathematical notation. This is Liz notation, but 3 terms, right? Do you see those 3 terms? And we know what the factors of those are. In algebra basics, you would have written down 8 and x, 22 and y, and -4. But of course, when we were looking for the lowest common denominator, we actually went all the way to prime factors. So maybe you're thinking of this as 2, 2, and 2, and x. The prime factors of 22y are 2, 11, and y. And the prime factors of 4, we could write as -1 times 2 times 2. And then literally, and it's cool if you've already finished this problem, I'm okay with that. Literally what we're going to do is we're going to say, which ones do they have in common? What are the factors that I can identify in every single term? And 2 is the only one there. The only factor that shows up in each of the 3 terms is 2. So I'm going to write that down. That is our GCF, our greatest common factor. Okay, what's left over? What happens when we extract 2 from each term? Well, here I have 2 times x, or 4x left. Here I have 11 times y, or 11y. And here I have -1 and 2, or -2. And we're done. There's no other pattern on the inside, but we will be starting to check. So we find the factor that was common to all of them. We did that. I skipped over this a little bit. I said we extract the 2. What have we really done when I pull out a 2 like that? I just yank it out. I'm really dividing. So 8x, when we yank out a 2, we're really dividing by 2. 8x divided by 2 is 4x. The 4x then is our leftover that goes in there. So you certainly do not need to write out the prime factors this way. In fact, if you can see the answer just looking at the original, go for it. I completely understand. The goal is for all of us to get there. But if you're ever stuck, writing down the factors of each term can be very helpful. For the second one here, what's the greatest common factor?
3x squared y.
3x squared y. So one thing I want you to think about is when we were in algebra basics, we were only concerned with denominators, and we were always looking for multiples. We were looking for the lowest common multiple, the lowest common denominator in that case. So if we looked at the x's, we always chose the biggest one, because when we were looking for the LCD, we were looking for a larger number that I can divide by each term. We're doing the opposite now. The greatest common factor is the biggest thing we can remove. So if I'm thinking of these two terms in terms of how many x's they have, well, we have 3 in the first one and 2 in the second one. I can't remove more than I've got. So x squared is the largest number of x's I can remove, is the greatest common factor. So just where it goes. The best cat ever has joined us. Lovely. What have we got left over?
X minus 8y.
Yeah, x minus 8y. How do you know you're right? What's lovely about factoring is you really don't need me to tell you what the answer is. You can check every single answer by using distributive property. You simply take the 3x squared y, multiply it by x. Do you get 3x cubed y? If the answer is yes, you're good. If the answer is no, revisit what you've factored. And of course, 3x squared y times -8y gives us -24x squared y squared. And if you can do that, we can do a whole series. So you'll see that I've poached these ones from my lab. These are all from the review. And all I really want to do with these ones, I have a slightly different reason for putting each one up here. I just want to talk about a couple things. And the first is that a question that looks like this is sometimes hard because it's really easy. Sometimes when we're factoring, there's really not a whole lot that we can do. So if we take 4x plus 8s, what does that look like in factored form? What is the
factor by 2?
Yeah. Oh, you can go bigger. But if you take out a 2, it'll be more obvious.
I mean, 4.
Take out 2, yeah, then we have 2x plus 4s. And if you don't find the greatest common factor in the first go, that's okay. You can keep going. So let's pull out another factor of 2. So that gives 2 out front, and we're left with 4 plus 2s. 2 times 2 is just 4. So we have x plus 2s as our leftovers. If you go straight from here to here, that's fine. This is definitely a one-step question. I know you're going to ask me about intermediate steps. You can't really write anything down here, so don't worry about it. So sometimes the easy ones throw us. That's really what I want to say here. Those letters are not the same. You're not going crazy. This one's fairly straightforward, but I actually want to look at this last one because it's worth discussing anything that's got negative signs. And the numbers are a bit bigger. So first of all, what might you write down as the greatest common factor?
8x square y.
Yeah. So you don't have to go all the way to prime factors. 72 is divisible by 8, 32, 40. Yeah, I can see that they're all divisible by 8. So I might just have thought this or written this down. And then, yeah, the largest number of x's that we can remove is governed by the smallest number of x's we've got in any single term. And same with the y's, so that's governed there. And then we've got some leftovers. As soon as you have the GCF, write it down. Don't throw it away. That's the biggest mistake I see. You find the greatest common factor, you chuck it, keep it. What's left?
Minus 9xy cube plus 4y square minus 5x square.
I like it. And now that I have fewer things, I have fewer factors in each term, I usually, have a quick look at it and say, do I have anything that I missed? And these x's make me feel like I missed something, but there aren't any x's left in the middle term. A fair question here would be to say, but I've got some negative terms out here. So I want to talk about what happens when we have negative factors. You might have said, because we start with a negative, because our first term had a negative value, you might have pulled out negative 8x squared y. In which case, what happens to the stuff on the inside? Right now you have negative 72 divided by negative 8. So you have positive 9 xy cubed. Positive 32 divided by negative 8 is now negative 4y squared. And the last one is positive as well. So you might have done that, and that would be okay. So as long as you're consistent, what you might notice is that really just every single sign changed. All the negatives became positive and vice versa. For this particular question, there are 2 negatives in the original. And regardless of whether or not I factor out a negative sign, I still have 2 negatives in the answer. So there's not a huge reason that I might want to do this. Either one of these would be perfectly fine. Doesn't change the number of negative signs. If I change this guy to negative, well, now I definitely want to pull out a negative. So if I have a negative for every single term, I would want to make sure I pull that out so that my answer has 1 negative sign and every other term within the brackets becomes positive. But what this also tells us is that I can mess around with negative signs. If I want to pull out a -1, I can. Why would I do that? Well, I would do that if it reduces the number of negative signs, or if it helps me to simplify the rest of the problem, right? If I have some context here, maybe pulling out a negative is helpful, and we will absolutely see that. So negatives are a little bit tricky. And then the last bit is just a bit of a cautionary tale. There are a couple different ways to factor this problem. Try it based on what we just talked about. Use the same strategy that we used for the previous ones.
Four x into x plus 1 into 3 minus x.
Yeah. So what looks like you've done is you've looked at those 2 terms, you've recognized that you have 2 terms, and you've looked for the common factors. 12 and 4, well, the greatest common factor is 4. The most we can take out is a single x when I compare these 2, and they both have an x plus 1, a factor of x plus 1. Once I remove those, what's left over? 12 divided by 4, x divided by x plus 1 divided by x plus 1, I do just have 3. And in the second term, all I have left is an x. There's no good reason for me to use square brackets except to highlight it for us as we talk about it. So those can definitely be round brackets. If you decide to expand first, you'll get to the same point. So if you decided to just expand 12x times x plus 1 by using distributive property, that's okay. But it's much faster if you take out the common factors first. So it's a handy trick for expressions that look like this, right? Just so that we have as many tools as possible. This tool right here of taking out the greatest common factor without expanding is really helpful when they're uglier, right? When our powers get larger, I don't want anybody to expand this. That's a lot of work. That's 4x minus 3 times itself 8 times. Don't do it. Just leave it. The question here doesn't say expand. Actually, it doesn't say anything. So I suppose you could do whatever you like, but we're factoring. So try just that first one. I think I did okay based on your nodding. Awesome. It's good when two of us have the same answer. And so I just said, here's one term, here's the other. What do they have in common? I looked at the numbers 24 and 16. I looked at the x's, x to the power of 3, x to the power of 6, and then finally the factor 4x minus 3. There were 8 of them in the first term and 5 of them in the second term. This particular question I am calling done. Stop. I don't know if it's tempting. It's not tempting for me to expand 4x minus 3 to the power of 3. You could, and it's possible you could simplify a little bit. You would get another term that's 2x cubed somewhere in there, but you're just going to end up with a whole series of terms that are not like. I would leave it. Here's my rule of thumb for you. If this was just 4x minus 3, that's pretty easy to simplify. That's just distributive property. Go ahead and write this as 12x minus 9 minus 2x cubed. So if it's easy to tidy up like that, go ahead and tidy it up. But because this one is actually to the power of 3, and that's an awful lot of work, that's not going to bring us anything. Let's not do that. And that's both practical in the test sense and practical in that's probably not going to help you solve your problem any more than it did before. So this is a 3. This is a really ugly 3, sorry. Let's leave the answer that way. I'm going to skip over just the 1. That's common factoring. It's basically, again, something we're going to talk about every single question. So here's a pattern I know a number of you have mentioned that you're seeing already, and that was from the exponents and radicals module where we were interested in creating this pattern. In exponents and radicals, when we were trying to rationalize the denominator, when we had, for example, root 3 plus root 2 as our denominator, let's say it's 1 over, and we wanted to get rid of the radicals from the denominator, we said, all right, we can do that by multiplying by the conjugate. Every single time we did that, so of course, top and bottom has to be multiplied by the conjugate. Every time we did that, we found that we ended up with perfect squares under the radical. Root 3 times root 3 is 3. Root 2 times root 2 is 2. And the middle two terms canceled out. So every time we have this scenario, a plus c, a minus c, we end up with just the square of the first, a times a, and the square of the second. So we were interested in going this way. We're factoring now. We're going to go the other way around. So when we see this pattern, a perfect square, and a minus sign between them, we can now recognize that their factored form are 2 conjugates. The square root of the first, square root of a squared is a, and the square root of the second, square root of c squared is c. So I'm just going to do this next one on the next slide, and we don't have to do all of these, but you'll see the pattern quite quickly. X squared, or x plus 2 times x minus 2 is x squared minus 2x plus 2x minus 4, or ultimately x squared minus 4. X squared, x, ahead of myself. X plus 6 times x minus 6 is x squared minus 6x plus 6x minus 36. Even if it's more complex, even if we have a coefficient other than 1 in front of the x's, and complex here is extremely relative, it's not really that complex, unless I put in a 2 instead of a 1. So if we're comfortable with the pattern in the direction we've been working it, I think we can probably go the other way as well. So recognizing that if I see a perfect square, and a minus sign between them, the square root of the first thing, so the square root of x squared is x, the square root of the first thing will be the first term in the binomial, the square root of the second term, the second thing, square root of 4 is 2, will be the second term in each binomial. One gets a plus, one gets a minus. This pattern is called a difference of squares. Perfect square, minus sign between them. So if I take x squared minus 9 and I want to this time write the original, what is the factored form of x squared minus 9?
X minus 3 into x plus 3.
Yeah, the square root of x squared is x. So the first term will be x in both binomials. The square root of 9 is 3. One gets a plus, one gets a minus. If you don't believe it, write in that middle step, going in this direction again. It absolutely works out. And we've seen it in much more complicated examples, because as soon as we put in radicals, it looks messier. The only trick I can throw in with a difference of squares is to hide them, or to just ask you to do steps sometimes in different orders. And question number 1 is a good example of just hiding it. I see 2 terms. What should I be looking for? Is it a difference of squares? Not really. I mean, maybe the answer is eventually. Maybe that's why you're having trouble answering me.
We should take 2x outside, and then
As soon as
it
I
will
look at
become
this,
square.
exactly. Sorry to cut you off before the big reveal there. Yeah, I was very focused on taking out the 2x first. And then we will see a difference of squares once we've removed that common factor. So as soon as I look at any expression, I'm looking at this one and saying, aha, I have 2 terms. My first question is always, do they have any factors in common? If the answer is yes, pull those guys out first. So pulling out a 2x leaves me with x squared minus 25y squared. As it was written originally, that was not a difference of squares, right? 2x cubed is not a perfect square. In no world is 50 a perfect square. You can take the square root of 50, but you get a decimal, and that's not what the definition of a perfect square is. That's not what we're interested in here. We're in algebra, no decimals. Now, if you see the difference of squares, just don't forget to drag that greatest common factor along with you. Don't make that equal sign a liar. Right? Every line does really have to be equivalent to the one before it. But I recognize the pattern here as a difference of squares. So I get x plus 5y and x minus 5y. Is the second one also factorable? Different approaches here that would work. I can think of two. Maybe you've gone ahead and taken out 3. 3 and 27, both divisible by 3. So you've taken out 3 and you're left with negative x squared plus 9. Or maybe you decided to remove negative 3 because the first term is negative and we just don't like the look of that. It's awkward. So maybe you took out negative 3, in which case you have positive x squared minus 9. Both are factored. Both have the greatest common factor removed. I think the one at the bottom is easier because it's immediately obvious to me that I have a perfect square in the bracket, in the leftovers. Perfect square, minus sign between them. Get x plus 3, x minus 3. But all is not lost in this first one, right? You can play with that too. It's not a perfect square the way it's written, but I can just take this first term and the second term and have them flop sides. I can move terms around. We do that all the time. We can move terms around as long as you keep the sign with it. So as long as the 9 is still positive and the x squared is still negative, you can have them switch position. And now I see another perfect square, minus sign between them. It's a difference of squares again. I get 3 plus x and 3 minus x. They're both a perfectly good answer to the original question. They're both equivalent to the original. They're equivalent to each other. What I do want to think about is really what's going on. So I've got 3 plus x. Is that the same as x plus 3? Yeah, positive x, positive 3. It doesn't matter what order I write them in. The one thing that is a little different is that 3 minus x, is that equal to x minus 3? Sort of, not directly, right? 3 minus x, I can't just flip those two numbers and leave it at that. I've got a positive 3 in one and a negative 3 in the other, a negative x in one and a positive x in the other. The only reason that this works is because of the negative. So if I don't like that it's 3 minus x, and I'd like to write my x as the first term, which we like to do. We like to put all our variables up front and then our constants at the end. So if you'd like to rewrite 3 minus x so that the x comes first, we can do that. You can rewrite this as negative x plus 3, keeping the signs with the term they belong to. And then what you can look at here is nobody likes a negative initial term. So let's factor out a negative. Let's take negative 1 and divide both terms by negative 1. Negative x divided by negative x is, or by negative 1 is positive x. Positive 3 divided by negative 1 is negative 3. So this is going to be a handy tool that we can use. If it looks better, or you could simplify if you had everything in the same order and you end up with something that isn't, flip it. It doesn't matter here for this question because it's a standalone, there's no context. But these are all tools at our disposal when we go to simplify and to solve equations. All right, what about that third one?
Both are perfect square.
Yeah. Or sorry, I missed it. I think I heard what I wanted to hear.
It's perfect square.
It is, yeah. So it is a difference of squares. The square root of x to the power of 4 is
X square.
X squared. Because it's x to the power of 4 to the power of a half, which is x to the power of 2. However you think about it, the square root of x to the power of 4 is x squared. So we get x squared plus 1 and x squared minus 1. Are we done? You should always ask yourself
Not yet.
Sometimes the answer is yes, and sometimes like this one, the answer is no. because x squared minus 1 is also a perfect square. X squared plus 1, that's not interesting. That's a sum of squares. It's not a pattern that is factorable. But this guy, x squared minus 1, the square root of x squared is x. The square root of 1 is 1. 1 gets a plus, 1 gets a minus. We can absolutely keep going. So this question is really there. All of these are there to say, do whatever you see first, go for it, then reassess. Whatever is left over in those brackets, check that it doesn't fit another pattern. But what about the last one? Go ahead and give that one a go. And you have different approaches here. All of us will end up taking 2 steps to get to the final answer. Maybe you followed my advice and the first thing you looked for was a common factor. 4 and 36 are both divisible by 4. And then we had a look at the leftovers inside the brackets, x squared minus 9. That is a perfect square. So we're left with 4. And then x plus 3. The square root of 9 is 3. Math hasn't changed. And x minus 3. Or maybe you looked at that and said, hey, that is a difference of squares as written. 4x squared, perfect square. 36, perfect square, minus sign between them. So it does fit the pattern. So we'd have 2x plus 6 and 2x minus 6. But, and that's fine. That's valid. We're just not done yet. Now we look inside the brackets, and what I notice is that inside the first bracket, 2x plus 6, I have a common factor of 2. So I take out that common factor of 2, and I'm left with x plus 3. And then inside the second bracket, I'm also left with a common factor of 2. So I'm going to take out the 2, and I'm left with x minus 3. And may as well multiply those two 2's together. They're both just hanging out there, regular numbers in front of the brackets. 2 times 2 is 4. So we get exactly the same answer. My argument is generally that that's easier for a number of reasons. 4 and 36 aren't very big numbers, but if your numbers are bigger, taking out a common factor will shrink them down, and smaller numbers are easier to deal with. And it feels a little more awkward to me to take out common factors from both and then multiply them together. I could have just taken out the common factor at the beginning. There's no wrong answer. They're both valid as long as you get the same final answer. How you get there isn't all that important. But I do think that this first approach is a little tidier. I mean, for question 1, we had to take out the common factor first, right? It wasn't a difference of squares until we removed the greatest common factor. Then we saw a difference of squares. This is just different, where it's a difference of squares, whether or not you pull out the common factor first. All right, so let's get into the heart of it. As soon as this is responding to my wishes again, we will go, there we go. Let's do trinomials. Most of these will be quadratic or related. So we're looking at the form. This is just an expression, so a quadratic expression, ax squared plus bx plus c. We'll see that the x's are in order of descending power, x squared, x1. This is really x0. So we want to make sure that they're organized that way. If they're not, just reorder. And the two big scenarios we need to address are, what is the value of a? The simpler ones to solve are where a is equal to 1. So where we just have x squared plus bx plus c. So we'll start with those ones. And then we'll look at what happens when a is a value other than 1. Of course, a cannot be equal to 0, otherwise it's not quadratic. Otherwise, this whole term is missing, and it's just a regular old expression. So a can't be equal to 0. I don't know that why not go through this whole series? I was about to say I don't know that we have to do this, but it doesn't hurt, and it's fast for us to do. So we're going to start again in the direction we're super comfortable with, which is expanding. All right, so these are all in factored form. So I have x squared plus 5x plus 3x plus 15. And hopefully not surprisingly, the middle two terms are like. So as a final answer, I get x squared plus 8x plus 15. Try the other three. Just write them out across the page, just so we can compare them and look at their patterns. And our answers all look very, very similar. Mostly the same numbers with differences in sign. All of them have an x squared, 1x squared specifically, as the leading term. And those all came, in every single case, came from x times x. X times x is x squared, x times x is x squared, x times x is x squared. They all came from the same place. What we're doing here is foiling each one, first, outside, inside, and last. So the first two is x times x. And then we have two options for the final term. We had positive 15 for the first two. That came from positive 3 and positive 5, or negative 3 and negative 5. In each case, that's where the 15 comes from. But in the last two, that's the only case where we have opposite signs. So on the left, we have the same sign. On the right, we have opposite signs. So we ended up with negative 15. Negative 15. What I do notice as well, regardless of sign, is that the first term, the x squared, is going to determine the first term in the binomial, or rather the first term in the binomial determines the first term of the trinomial. And this last term of the trinomial is dictated by the last term in each binomial. 3 and 5 are factors of 15. And of course, x and x times x, are factors of x squared. So the only numbers I see in the brackets are factors of 15 and factors of x squared. How do we get the middle number? Where does the middle number come from? That's always going to be the question in these ones. So here we have 8x and negative 8x in the first two. They're a little bit different from the second two where we have 2's. So if I have x times, that was horrid. Let me go back. The outside 2, x times 5 is 5x. The inside 2, 3 times x is 3x. That gave us our like terms, and 5 plus 3 is 8. So the middle number is a sum. In this case, of course, because our signs are negative, we have negative 5x and negative 3x. So we ended up with negative 8x. In both cases, we got that positive 15, because when our signs are the same, we'll always end up with a positive answer. When our signs are different, we end up with a negative final term. So now we're adding two terms in the middle here that have opposite signs. So sometimes we get a negative middle term and sometimes we get a positive middle term. So I'm noticing the signs and where they're coming from. At some point, we have to actually solve a question. So I'm going to leave this. You have it in front of you as well, and go to actually doing. Should have hit save a little earlier. There we go. There are lots of tools for factoring. Where we've got a 1 in front of the x squared, we don't really need any of them. We're always looking for the same thing. I recognize that I have a quadratic trinomial, x squared, then an x, then no x. So I know that I'm going to have two binomials that are factors of it. In factored form, it will be two binomials. I know that my only options are to put an x in this first spot. Only x times x gives x squared. But what are your options for the second location? What are your options for the numbers?
6 and 2.
They have to be 6 and 2, and the only options are based on the 12. You can only use factors of 12. So that's why 6 and 2 is perfect. So factors of 12 would be 1 times 12, 2 times 6, and 3 times 4. You get those are your only choices. Why 2 times 6? Because 2 times 6 is in fact 12, but 2 plus 6 would give us the 8. So we're going to have x plus 2 and x plus 6. So we're looking for two numbers that when I multiply them give me the third term, but when I add them, they give me the coefficient of the middle term. Every single time. So here, 12 again, I'm still got the same options. So it could be 1 times 12, 2 times 6, or 3 times 4. But this time I need them to add to give 7x. So
3 times 4.
3 and 4. 3 times 4 gives us the third term, and 3 plus 4 gives us the coefficient in any case of the middle term. So those were all positive examples. Here, the next two, you see I always have these in pairs. They have a positive final term, and now we have a negative middle term. So I already know what the signs are going to be. The only way to get a positive last term is to have positive times positive or negative times negative. Here I know it has to be negative times negative because that's the only way I'm going to get a negative middle term. So I really have no options here. If x minus 2 times x minus 1 doesn't work, it's not factorable. Generally, everything I give you is factorable. We don't have to stress over ones that cannot be factored, but of course, there are countless examples of quadratic trinomials that you cannot factor, right? I think this unit makes it seem like you can factor all quadratic trinomials, and that is far from the truth. Have you done the last one? This is kind of the first one where we've got a coefficient other than 1 in front of the x squared, but we do have a common factor. In order to factor completely, you're going to have to pull out any common factors at some point anyway, so you may as well do it at the beginning. It may as well be your first step. And in this particular case, we end up with one of those simpler trinomials where we have a coefficient of 1 in front of the x squared. So we can move a little bit more quickly here. Let's do this guy. It's not quadratic, but at least it's a trinomial. But what I really don't like about this question is the negative in the first term.
minus 3x into x minus 3 into x plus 1.
Yes. So in this case, when I pulled, because there was only one term with a negative, in this first step, when I pulled out a negative, I actually created 2 additional negatives. So if this was all I was going to do, that's not ideal because I haven't reduced the number of negative sides, I've increased them. But all of the trinomials we looked at had a positive coefficient for x squared, and those are the easiest for us to factor. And if they're part of a larger question where we're simplifying or we're further solving an equation, it's just easier if all of them have a positive coefficient. So that's what we tried to engineer. So I pulled out the -3 instead so that I would have this positive coefficient for the first term. And then all I had to look at was the fact that this trinomial, can it be factored? Yes, it can. -3 times +1 is -3, and -3 plus +1 is -2. I just want to talk about the first one for a moment because sometimes as soon as the numbers get bigger, and 48 is not that big, but if they get bigger, it can be harder for us to come up with the factors. Here we're looking for 2 numbers that when you multiply them, give you 48. So we're looking for factors of 48, but when you add those 2 numbers, they better be +2. Because the last term is negative, I know one will be positive, one will be negative. And because it's a -48, I know I'm looking for one positive number and one negative number. If your mental math escapes you and your times tables escape you, go through it slowly. To find all of the factors for 48, I'm going to start by dividing by 1, then dividing by 2, then dividing by 3 until I found all of the factors. It's a bit brute force, but if you cannot, if you're stuck, this is a good way to try to find the numbers. 48 divided by 1 is, of course, 48. So those are 2 options, not useful ones, but they're options. 48 divided by 2 is 24. If I divide it by 3, it's 16. 3 times 16 is 48. 48 divided by 4 is, of course, 12. 48 divided by 5 doesn't work. 48 divided by 6, that works, and it's 8. 48 divided by 7 doesn't work. 48 divided by 8, well, now I've gone around the corner, so I know I've found all of the factors of all of the pairs of 48. These are my only choices. Again, because it's negative, one will be positive, one will be negative. So I'm looking for 2 numbers that have a difference of 2. So it must be 6 and 8. So it has to be 6 and 8. Which one's positive? Well, I have a positive middle term, so the bigger of the 2 numbers must be positive, and the smaller of the 2 must be negative. If you're not sure, look at the outside, that's 8x. Look at the inside, that's -6x. Yes, those sum to +2x. This inside-outside piece is really important in the next set. I'm going to skip all of those and go right to the worst ones. Last topic for today, just to get started with these ones. Still trinomials, still factorable as 2 binomials multiplied together, but in no case will a be equal to 1. So the leading coefficient will be other than 1. Of course, this would be 2x squared minus 3x plus 2x minus 3. And so as a final answer, we'll have -x minus 3. And I just do this first one to really highlight the problem that we run into. Because the leading coefficient is no longer 1, it will never be true that we're looking for 2 numbers whose sum is negative, or back up, whose product is -3 and whose sum is -1. There are no 2 numbers that multiply to give -3, but add to give -1. And that's because the 2 is, of course, involved as well. The 2 is active as I do the FOIL. right? So we had, sure, x times -3, that gave us the -3x, but here we have the 2x acting in the middle. 1 times 2x is where we get this 2x from. So it affects the middle term to have that 2 out front. This one here, again, 6x squared plus 9x plus 16x plus 24 gives us 6x squared plus 25x plus 24. And this one actually looks like we might be able to factor it by completely ignoring the 6. But there's no way that's going to work. We know there's nothing we can do to make that happen. What I do want to point out using this last one is using both of them really. So here, this is 1 times 2 is 2. Here we had 3 times 2 is 6. So the coefficient of the first term is going to tell me what numbers I'm allowed to use in my binomial. Similarly, the coefficient of the last term, the -3, gives me the parameters for the second in each bracket, the second value in each bracket. So here we have 24. That's where the 8 and the 3 work from. So again, as before, it's really only the first and the second that give me the options. They limit the number of, or the different choices I have for the numbers inside the binomial. And then I just have to make sure they work out for the middle. There's lots of good tricks here. We're going to start trick-free first. We're going to start without tricks and just analyze each one. So starting with this guy. So the leading coefficient is 5. This one's not quite as easy as the others, but at least 5 is prime. The only way I get to 5 is by having 5 times 1. So 5x and x are really my only options. 5x times x is 5x squared. There's no other way to do that. And as for the second number, well, that's going to come from here. I can only have 2 and 1. It's the only way. Those are the only factors of 2. It's the only way I'm going to get to that 2. My only question is which way around do they go? So if I have 5x and x, I can put the 2 and the 1 in this order, or I could do them in the opposite order. Those are the only 2 ways I can organize that collection of numbers. The 2 is positive, the 7 is positive, so at least everything's positive. Could be worse. My only question for you now is which one is right? Which one is actually the answer? So to check, I know that 5x times x is 5x squared and 2 times 1 is 2. We organize that. Okay, I organize that. So I'm not really checking those, but I'm interested in making sure I get the 7x. 5x times 1 is 5x. 2 times x is 2x. 2x plus 5x is 7x. So that is the right answer. The other one is wrong. So you don't have to write both of those down, of course. How do I know this is wrong? Well, I already found the right answer, but also 5x times 2 is 10x, and 1 times x is just x, and x plus 10x is not 7x. So there's no chance here. So that's what I'm doing in each scenario. Because we're a little snug on time, I'm going to skip us to something slightly more challenging. And the problem with this one, we'll do this guy first, or possibly only, is that now we're starting to have more options. 8 is not prime. I still know that I'm going to have 2 binomials, something x and something x. And the numbers for those somethings are 100% determined by the 8. So it's either 8 and 1. So it's either 8x and x, or 4 and 2. So 4x and 2x. So now I have more than 2 options to try. At least the third one is prime. I only have 3 and 1. So this is either going to be 3 and 1 or 1 and 3. Same thing here, 3 and 1 or 1 and 3. So we have 4 different options we need to try. So this is the guess and check part. See if you can visualize what's going to happen. And I would encourage you to really show where those outside and inside numbers are coming from, the ones that are supposed to add up to negative 2x. We need to organize 8 and 1 and 3 and 1, or 4 and 2 and 3 and 1 in some way that the outside and the inside will give us negative 2. And you know when you've got it, because you'll be able to do the multiplication to get back to the original. Lots of things I'm paying attention to, though. I'm also paying attention to the fact that I have a negative 3. So either the 3 or the 1 will be negative. And the middle number is negative. So here I have 6x and 4x, but I want the middle number to be negative. So I'll need negative 6x and positive 4x. Positive 4x times positive 1, that would do it. Positive 2x times negative 3, that would give me negative 6x. So that's the organization you're going to need. Super quickly, this is the part where there are lots of tricks that will help you to come up with the 4 key numbers, that will help you to come up with those 4 numbers, 4, 3, 2, and 1. One way to do it very quickly is to take A and C, so the coefficient of the first term, the 8, and the last term, the negative 3, and multiply them together. So we have negative 24. Underneath that number, I want you to write B, the middle term, the coefficient of the middle term, so negative 2. So first and last, A and C, and then the middle coefficient. I want you to now come up with 2 numbers that when you multiply them give you negative 24, but when you add them give you negative 2. And the answer will be 6 and 4. So this will be the leap of faith you need to take. Negative 6 times 4 is negative 24, and negative 6 plus 4 is negative 2. This is the hard part. This is your biggest job. Now, the rest, you're just going to follow these steps. You're going to divide both numbers you just came up with by the coefficient of the first term. So in our case, we're going to divide both by 8. Now you're going to take both fractions and simplify them. Negative 6 divided by 8, those are both divisible by 2. So we get negative 3 and 4. And I'm going to put that negative. I'm going to make sure the negative is still with the 3 because it came from the negative 6. And 4 over 8, that's both divisible by 4. We get 1 over 2. Have you seen those numbers before? Absolutely. Those are the numbers that you're allowed to use in your brackets. The negative 3 and the 4, the negative 3 and the 4 go in the same bracket. The 1 and the 2 go in the same bracket. Because we divided by the coefficient of the first term, you can remember that that came from x squared, so you can put a little x there. That's why it's the 4 and the 2 that will be the x terms. So that's in the video I posted about this, it's called the diamond method. It has lots of other names and slight variations. It works really nicely. If you're having trouble coming up with the numbers that you need, the combination of numbers, I should say, that you need, this is a quick and dirty way to do it. It has some caveats. If A and C are big numbers, then their product will be a really big number. So sometimes your numbers get really out of hand here. And this, if you did not remove a common factor before you started, this will not give you the correct answer, right? Because you're reducing, you're going to eliminate the common factor in that reduction. So you have to be really careful if you're going to use this trick that you first remove a common factor, that you first factor out the greatest common factor. This one will work only, these are how to factor these trinomials, yeah. There's lots of other things we can factor, could factor. These are the only ones we're going to do. So we could factor cubics, and then you have related tricks that will work as well. If maybe you like to do factoring by grouping, maybe you split up this middle negative 2x. Maybe you're doing 8x squared minus 6x plus 4x minus 3, and then grouping those. That's absolutely okay. If you want to cover that as a class, we can. If you're just happy doing that method, go ahead, keep doing it. That's completely acceptable. So if you already have a favorite way to factor, keep doing that. If your way isn't working for you, maybe it's time to switch it up. But those are very, very quickly a couple more ways to tackle these problems. So on Thursday, we're going to tackle more of these harder ones, mostly so that we can talk about the different methods. Factoring is a bit tricky, and it just takes practice. So you won't have a ton of time to practice before tomorrow, but you'll have time to practice before next week, certainly. If it's something that you really need a refresher on, this might take a little bit of practice. It's certainly one where you either get it or you don't. For a long time, it doesn't work, and then it'll click for you. I promise it will. It always does. But there's always an element of guessing and checking when we factor. I can't tell you the steps in quite the same way. Even in this trick, we had to come up with the numbers -6 and 4. You have to try possibilities and see what happens. Also tomorrow, though, we will be using factoring to do that simplification and solving equations as well. So we'll get more practice together, both as just expressions and in application. But for today, we got through. 4 classes will be enough. I just wanted to get as much done today as we could so that at least we have big picture about the types of problems I'm going to ask you to factor. And we really pretty well covered all of it.